Good morning, everyone, and welcome to today's Tech Talk. I'm Janki Gattu. I work with Geosys Enterprise Solutions Private Limited as a GIS specialist, and Geosys Enterprise Solutions Private Limited is an ISRI partner company and an ISO 9001 and 2015 certified organization. In today's Tech Talk, we are going to discuss about predict floods using GIS. So let's understand the background about this particular topic and why we have chosen today. We are going to discuss about an area called Stowe, which is a small town in Vermont state in United States. If you see here in the image, in the northeastern portion, can you see a red mark here? And this is where Vermont state is located in the northeastern region of the United States. And I will show you here in the Google Earth. This is our United States, and if you come here to the northeastern area, this particular state is our Vermont state, and here we have a town called as Stowe. And today we are going to discuss about this place and what happened to this place in the year 2011. So now I'm zooming to the location of our area of interest. If you see here, you have a lot of hilly areas and terrain areas which you can see clearly in the image. And this particular town is located in the downhill of this area. Okay. So this town is a small town in Vermont state and it has merely 5,000 residents. And in the year 2011, on August 28th, there was a Hurricane Irene struck. If you see here, you can see the Irene struck here. So you have seen like how devastating that particular year is for Stowe area. And because of that floods, all the roads, buildings, bridges, culverts, everything washed out in that area. And because of that reason, the officials in that particular town, Stowe officials, they understood that they have to have some planning so that they can actually prevent us from further floods. So for this, they had little information about the flood prediction in that particular area. So where they have used something called as line graphs, and they identified how much of water is being flowed, at what speed the water is being discharged during the rainy season, and at what time or at what interval we can get the floods. So all the studies has been made by the Stowe officials after this devastating flood within Stowe area. So in today's topic, we are going to see how we can create hydrographs. So, and the agenda for today is we are going to see how we are going to use our distal elevation model, and based on the distal elevation model we are going to demarcate a watershed boundary, and from that watershed boundary we are going to understand at what speed the water is flowing by using a field called as velocity field, and then we'll understand the path in which the water is flowing using water flow path, and finally we'll be creating a unit hydrograph. And why this floods are being occurring very frequently in that area is because of the extensive development that has been taken place in that area. There are like a lot of construction activities going on during the previous years when this particular incident has occurred. As such, there were a lot of constructions that were happening, and which finally has led to this flooding. So in order to prevent this flooding going forward, the Stowe officials has taken some steps by using this process, and they have identified the areas where it is more prone to floods, and they have created the unit hydrographs for it. So let's understand how we can work on this 5 steps today. So before we go forward, let's understand the basic terminology that we are going to use in today's Tech Talk. So the first input for us, in order to predict the floods, we need the highs and lows of that particular earth surface or our area of interest, which is tau. So in tau area, we need the highs and lows of that particular area, for which we need x, y, which is location, and the z coordinates of that particular location. So we can get that z elevation using a raster layer called as distal elevation model. So distal elevation model is a type of raster GIS layer. And what it will show here, if you see here in the colored image, you can see only the bare earth, and you are not able to see any buildings, any trees, or any other surface objects. It is only showing you the highs and lows on this particular earth surface. And when you see this distal elevation model in our software, either in our ArcGIS desktop or in ArcGIS Pro, you can see the distal elevation model in the form of grids, which we call it as raster grids or cells. And each cell will have a elevation value. And if you want to know more details about a very small area, you need to really have very small grid spaces. So when you zoom to a particular grid space only, you will be able to understand more details about that area. So we are going to take this distal elevation model as an input for tau area, and then we are going to proceed with the further steps of analysis. And generally, where do we use this distal elevation model? For line of sight analysis, which means, let us suppose you take a top of hill and you stand on the top of the hill and you want to see what area you can see from there. You can see the area which we call it as line of sight, but you cannot see what is under that particular mountain. Right down the mountain, you cannot see what features are there because your line of sight doesn't allow that. But you can see farther places which are far off from you. So that is called line of sight analysis. So when you take distal elevation model, you can do line of sight analysis. You can use this as a base map for identifying the elevation, highest and lowest surfaces on the earth surface, and for precision farming, and then surface analysis and water flow analysis. So in hydrology, so there are like different applications where we will be using this particular distal elevation model. So let's understand the technical terms now, what we will be using in the analysis. So here, basically this distal elevation model is a raster GIS layer, as I told you earlier, and it is formed in the form of cells, raster cells, and it is a continuous data, which means each and every cell is connected. But when you have very highs and very lows on the surface of the earth like this, obviously the water that is falling on the roofs of the houses or on the mountains, it will obviously drown down into the seas or into the water bodies. But there will be places where the water completely drowns down into something called as sink, where the water will not flow anywhere from that particular place when sinks are created. So basically the sink is nothing but a depression. If you see here, the water is flowing because it is slant here, and at some point it has stopped. This is a depression, or this is a pit, which we call it as, which is obstructing the natural drainage flow, because from here the water cannot flow unless until it is at this particular level. Okay. So the flow path stops when a sink occurs. So when you take a distal elevation model, because of highs and lows on the surface of the earth, if you have very large differences between the highs and lows on the surface of the earth, then these sinks are formed. And when these sinks are there in your distal elevation model, you cannot take the data as a standard data for your hydrological analysis, which means you need to connect this properly. You need to reduce the errors in your digital elevation model for going ahead with the further analysis, for which you fill the sink. And you see this lavender colored one, which is a sink. And if you see here in the next image here, this is patched up here because we are filling up this sink with the elevation value of whatever is here. So we take the next elevation value at this point and then we match it here. So don't worry about how this is going to work. I'll show you when we are doing the demonstration. And the direction in which the water is flowing is nothing but your flow direction. And maximum number of directions in which the water can flow is only in 8 different directions. Why in 8 different directions? I'll tell you in a minute. Okay. And then flow accumulation. Flow accumulation means when the water is falling from roofs or from high level areas to the lower level areas, all the water will accumulate at some location. So that accumulation is called as flow accumulation. And the pour point. So what is this pour point? Pour point is nothing but the lowest temperature in which the water flows or any liquid flows. That particular point is called as a pour point. Let us suppose you take any kind of oil. Let us suppose you take a hair oil, and normally the state of that particular oil is liquid. If you are just pouring it onto the ground, it will normally flow onto the ground during hot summer seasons. But when the temperature is cold during winter seasons, right? So obviously you will not have that liquid consistency for the oil. That will be a semi-solid consistency. And even when you're pouring it, the velocity will be reduced, which means the flow in which the oil is coming down will be very slow when compared it within a liquid state, right? And if it has become solid, let us suppose you stay in the areas like Jammu and Kashmir where the temperatures are extremely cold, and obviously your oil it will not be in a liquid state, it will be in a solid state. And if you want to pour that oil onto the ground, it will not fall, right? But the last point in which the oil gets flowed, that particular point is called as a pour point, which means that is the last point in which the water or any kind of liquid will have its characteristics, and beyond that point, that flow will lose its flow characteristics. So here, if you see, the snap pour point is the minimum temperature at which the liquid flows is called as a pour point, and the minimum temperature at which the liquid loses its flow characteristics is called as a pour point. And the next one which we are going to see is about the isochrone maps. And what are these isochrone maps? Normally we use our Google Maps, right? Very frequently we are using these days to identify nearest bank and the direction in which I have to go. And I can also see if I have to go tomorrow at 8 o'clock, how much time does it take if I go by vehicle, if I go by walk. So within 5 minutes interval, what is the distance that I can cover? So all these kind of maps are called as isochrone maps. These isochrone map shows all the areas that you can travel from a given point location within a specified time frame. So I've seen one application just to tell you like how this works. If you see here, let's see how this generally works. I'm going to give our office address, GIS Enterprise Solutions Private Limited in Hyderabad. So this is my point location, and if you see here, it is generating something called as a drive time. We generally call it as drive time in GIS. And if you see here, this map is being generated for 30 minutes using public transportation, which means if you see here, this point is a point where Geosis is located, and within 30 minutes of distance, what is the distance that I can travel from here using public transportation is this all area till KPH I can cover on one side, Secunderabad on the other side, and Madhapur till Madhapur on the other side, and to this near to Begum Bazaar on the south side. So within So within 30 minutes, by using public transportation, this is what I can cover. Let us suppose I will reduce the time here to 10 minutes, and with public transportation, let us see how much area I can go. So if you see here, it is visible that within 10 minutes of distance using public transportation now, means at this time, you can barely go up to SR Nagar and towards Greenland Junction at Amirpet, and Mathura Nagar towards Yusuf Gouda, and near to Nagarjuna Hills on the south side. So if you change your transportation to driving, and if you still say that 10 minutes, you can see how much of area is being covered. So these maps which we are generating now, these are called as isochrone maps. Okay, so let's understand what is this a sink in the, as I told you, your digital elevation model is in the form of grids or in the form of cells like that, and each cell will have certain elevation value. Okay, and these are like sample elevation values which I have given you here for a digital elevation model. And if you see here, generally the water flows from the higher area to a lower area. If you see here, from 156, the water can flow to 144 to, from 156 to 134 and 156 to 148. Let us suppose the water is flowing from 156 to 134. And next, the water can flow from 134 to either 115 or 88 or 106, because it is the higher value and these are all the lowest values. But this cannot flow towards the upper direction because here you have higher values. So the maximum possible values are 115, 88 and 106. So, and now the water is here, and from here the water has to flow again towards its lowest value. But if you see here, here it has highest value 250, here it has highest value 160, here it has the highest value 110, and maximum where it can flow apart from this 3 blocks, it can flow here. So even if you see in all these directions, 98, 115 or greater than 88, 134, 106, 116. So in all these directions, the water cannot flow and the water is blocked in this particular cell. So this is called as a sink, where the water has flown to some extent and it got stuck somewhere and it stopped the natural drainage flow of the water. So this is what your sink is. And when you have a gap, obviously your water is flowing from here, and then you have a disconnect here, and then again your water is flowing from here to somewhere else. So in this data, you will not be able to do analysis because your data has some data errors as such that has to be corrected. So this sink has to be filled up. And how you will fill it up? It has to be the next value to the nearest cell. So here the nearest cell is, next to it is 250. So it should have a little more elevation than this, which it can be 250.1 as well. So this value, if it is 250.1, then the water flows from here to here, and then here from here it will not flow. So if it has a higher value, it flows here, and then from here it flows here. So this is called as your filled sink. Okay, so I hope you understood, and I'm moving on for the next slide. So if you have any questions, you please make a note of it, and then at the end of the session I'll be taking all your queries. So here I have given you an example. These are all the elevation points of my distal elevation model, and these are all the flow directions. So how the flow is taking place. So obviously from here it can go from here to here, or it can go from 156 to 134 as shown here, and 156 to 148. But how you are marking in only one direction? Why not in the direction like this, or why not in the downward direction like this? Is because you calculate the slope. And how do you calculate the slope for identifying this direction is, generally if you have a value next to it like this, which means not diagonally, but if it is next to it, either downwards or sidewards, then obviously you have to calculate the difference like this. Slope 1 is equal to, so you have 156 as the elevation value at one cell point and 144 value in the next cell point, divided by 1. Okay, or you can write it as 1, or you can just leave it like that, and here this will give you value as 12. Okay, and the next possible way in which your water can flow here is 156 minus 148. Again, it is downward direction, so it is 1. So if you take the difference, it is 8. So obviously the water will flow this direction, right? And now we will calculate the other direction, 156 to 134 here. In which direction does it flow? So slope 3 is equal to 156 minus 134 divided by square root of like 1 square plus 1 square, which is like square root of 2. So, and this value will give you around 15.5. So this is the value. If you see here, it has 12, it has 8, and it has 15.5. So the slope is more in the direction from 156 to 134. That is the reason you have the downward slope direction like this rather than the other two directions. In the similar way, you have to calculate slope from 144 to 138, 144 to 115, and 144 to 134, and then this direction flow is being formed. That is how theoretically how the water gets flowed from one cell to the other cell when the water is flowing. And if you see here, I have drawn the flow direction diagram, which we generally call it as a drainage diagram. And if you see here, the water is flowing from here to the next cell and here. So from here to here, and from there to downward direction. So here it is 1 and here it is 2. And from here it is flowing towards east direction. So this is the third one. In the similar fashion, I have drawn all the connecting points which will show me the drainage pattern in which the water is flowing, the flow direction. And how do I calculate the flow accumulation? Flow accumulation means the water where the water flows and accumulates, which means it comes and stays at one particular point. The water where it gets accumulated is called as flow accumulation. If you see here, the water is flowing from 156 to 134. As such, there is no water that is flowing into 156. As such, it is 0. In the similar fashion, from 144 the water is flowing, and there is nothing like water that is flowing into 144 cell here. So that is why it is 0. So if you see here, all these are 0 because those are the starting points of the water here. On either sides it is 0. And if you see here, this in 134 cell, the water is flowing from 156 to 134. So in only one direction it is, the water is flowing. So you have the flow accumulation as 1, right? And even from 144 to 115, if you see, the flow accumulation is only 1. If you see here, in this 106, the water is flowing from 148, so it is 1. 104 to 106, it is 2. And from 108 to 106, it is 3. And then 134 to 106, it is 4. And already there is a stream which is flowing from 156 to 134, which obviously is flowing here. So there are 5 sections here. So that is how the flow accumulation is being determined. So now, for me to proceed forward, As I told you, we are going to start with our digital elevation model, and then we are going to identify the sinks, and then we are going to fill the sinks, and then we are going to find the flow direction, flow accumulation, and then we are going to create a velocity field, and then we are going to create a unit hydrograph. So for processing with the digital elevation model, before we go ahead with the elevation here, first thing is when you take an elevation value, it has to be converted into, it has to be projected into a UTM coordinate system, or else you will not be able to perform any kind of analysis with the digital elevation model. That is the reason you are reprojecting the raster data to UTM coordinates after you fill the sink, and then you're going to remove all the errors, and then you're going with the flow direction, and then we will identify the sinks, and then we will fill in the sinks here. Okay, so here we are taking a digital elevation model, and then we are identifying the flow direction, and when we see the flow direction, we will see the places where the sinks are there, and if there are any sinks, you cannot do analysis, so you have to fill in the sinks for doing analysis. If there are no sinks, then you're going ahead with the existing DEM, but if you are having sinks in your DEM, you're going to fill the DEM, and then you're going to have this depressionless DEM, and then you're going to generate your watershed, your flow length, flow accumulation. So everything you will be generating from your DEM, which doesn't have any kind of sinks. So when I told you about watershed, what is this watershed? Watershed is basically the area in which all the flowing water will flow towards a certain point, and that point is called as a outlet point or a pour point, and the area in which all this water is being flown, that particular area is called as a watershed area. So we will be using our digital elevation model, as we have seen in the previous slide, to do our further analysis, and these are the steps that we have given you here, and I will show you all the steps when I'm executing the demonstration. And when I tell you a watershed, I know the water is flowing and the water is getting accumulated at a place, but I don't know at what speed the water is flowing, at what velocity the water is flowing towards that particular pour point. So what I will do is, because the water is flowing from one place to the other place, I am considering the water to be spatially variant, which means it moves from location to location at different places, but I'm not varying the time and discharge, but I'm just keeping that variant of time and discharge as constant, and then I'm going to work with this velocity flow. And here there are certain formulas and everything. When we work in the demonstration, you will get to know. And flow length is nothing but the length of the flow, the path in which the water is flowing, and the length of that particular path in which the water has flown, that particular length is called as a flow length. And all these are our inputs for generating our unit hydrograph. That is why we are discussing all this. And creating a water flow path. So as I told you, the water flow path means the route in which the water is draining from an area, and basically we call it as a runoff also. That particular path is called as a water flow path. And what is this hydrograph unit is? It is basically the hydrograph of direct runoff resulting from 1 unit depth of rainfall. So we take the rainfall also into consideration, and then we generate this unit hydrograph. You can see here, this is how the hydrograph is being generated with respect to the time and with respect to the discharge rate. So we will see how we can go ahead about this. So here, if you see, I have an ArcGIS Pro project which is open here, and I will turn off everything and I will show what data I have with me. So here we generally have a base map. So I also have a base map, which is topographic base map. And I am going to do analysis. As I told you, we are going to work with the Stowe area in Vermont state. So I'm going to take the boundary of Stowe, which is in Vermont state. And then I'm going to draw all the surface water bodies that are there here, which belongs to Stowe. So I'm going to create all this surface water body. So if you cannot see here, I'll just change the color. So this is the one which you can see here. These are the water bodies of Stowe. And then, as you know, for doing our analysis, we need an input called as a digital elevation model, which you can download it from USGS website, Earth Explorer. So I have my digital elevation model here, and using this digital elevation model, I'm going ahead with my further analysis. So when we are going ahead with this further analysis, the first step is precondition the elevation model. So what is this precondition the elevation model is? You're going to identify the sinks, and then you're going to fill in the sinks, and you're going to make your digital elevation model ready for your analysis. Okay, so let's see how we can work on this. So I have something called as tasks here, and these are the steps that we are going to use for creating the unit hydrographs. So the first thing is like precondition the elevation model. This is the first step. So if you see here the pop-up in this task, you will identify and remove all things from your digital elevation model. So let's open this and see what is there. So for input raster, choose your digital elevation model, because that is our input from which we want to remove the errors. So obviously you have to come here, and then the digital elevation model belongs to Stowe. So this is the digital elevation model which we have. And then we are going to calculate assess the flow direction. So obviously your output flow direction name has to be given here. So I'm going to give the Stowe flow direction as my output name. So let me go here. Let me go into this geodatabase, and I'm going to give Stowe flow direction, and I'm going to click on save. Okay. And here just this flow direction is a D8 type flow direction, which means the directions are only 8 directions, because if you see one second. If you see here, if you take one particular cell, let us suppose here, how many cells in which the water can flow? To 156, 1, 2, 3, 4, 5, 6, 7, and 8. So that is the reason we are taking that flow direction type is 8. The maximum number of directions in which this particular water can flow is 8. So we are taking that, and then we are going to click on run. And this is going to give us the access flow direction. We have to wait for a minute for the system to generate the output. So if you see here, this is where it is showing you the direction in which the water is flowing, and wherever you are seeing the darker areas are the areas I think like in which the water is flowing from the northern direction to the southern direction, from from steep areas to the narrow areas. And if you see here, the light ones are the ones like where the water is flowing towards the north direction. So that is the reason you have most of the image is flowing from north to south. That is the reason wherever it is towards the south, there you have wherever you have steeper slopes and wherever the flow is there towards the steepness, there you are identifying it in darker color, and where you don't have much steepness, there you have the lighter color. Okay, so now we finished our flow direction. Now we know in which direction the water flows. So if you see here, this is how this is the one which got generated, stow flow direction. Now the second step here is input flow direction raster to identify the sinks. So just now we have created the flow direction. Now we are going to create the sink for this. So I'm going to give the name and I'm going to click on OK. Okay. Stow sinks, and then I'm going to click on run. So this will generate an output which will show me the sink areas. Let us see what are those sink areas. Okay, so let's go back and see this stow sinks. Now I'm turning off this flow direction so that I can see it here. Let me turn off everything so that you will be able to see it clearly. Can you see here? There is a break, there is no connection because the data has to be continuous. Here, even if it is connected by one cell, also it is continuous. But if you see here, these cells are not connected, right? So these are called as sinks. So here, if you see, there is a gap. And mostly if you see where these sinks are mostly towards the stream. Wherever the stream direction is there, in those areas only you are having this sinks. So for our better understanding, what I will do is I will change the symbology so that you can see it better. So you can see here. Okay, so these are the sinks which we have identified after generating the flow direction, and we have identified the sinks. But as you know, we cannot do analysis if we have sinks like this in our data. So we have to remove these sinks and we have to fill in the data. So we have to fill in the data with the nearest nearest value, the greater elevation next to it. So what we are going to do is we are going to fill in the sinks here. So for filling in the sinks, here it is asking me to input the surface raster, which means the raster which we have to give here. In the distal elevation model only, we have to fill in that in the surface water. We have to fill in those sinks, and for this we are going to generate the output. So this is filling in the sinks. So I'm just giving the fill. Here I'm taking the distal elevation model and then I'm filling in the elevation values where it is missing. And this tau fill is the image or the raster which we will be using for further analysis, because this is the image which is free of errors. Okay, so let me click on finish. Okay, and this is our tau filled values. If you see here, these values are filled and it is almost similar to our digital elevation model, but you will not have those sinks here in this new digital elevation model. So by using this, we are going to do our further analysis. So I will just summarize what we have done. So we have used our digital elevation model and we have generated the flow direction. And with the flow direction, we have identified the sinks, which are stow sinks. And with the sinks, we cannot do further analysis. So we are filling in the sinks. And those filled sinks is our final digital elevation model that we are going to use with our next steps. So let's go and see what our next steps are. So we are done with the first step, precondition the digital elevation model. Now we are going to delineate the watershed. Delineating the watershed means you're drawing the watershed area. Okay, so for which there are like 5 different steps in this creation of the watershed. One is you have to assess the flow direction. So for assessing the flow direction, it is again asking us to give the input surface raster. So we are going to give that input surface raster. So what is this raster here? It is our new digital elevation model, which is our stow 12. And then we are going to calculate the output flow direction raster. So this will have the continuous flow in which the data is being flowing. So let me give the name as stow fill flow direction. Okay. So, and you know why we are giving D8? Because it has only maximum 8 directions. We are giving it as D8 and then we are clicking on run. And if you see here, it has given some random colored image, and let's go to the contents and see what is this stow fill flow direction. If you see here, it has given different colors in which the water is flowing. 1, 2, 3. If you see here, 1, 2, 3, 4, 5, 6, 7, 8. So the maximum number of directions in which the water is flowing is 8. So for each direction, the system has given some unique color, and that is the reason it has given a random color like this. Okay, so we need not worry about that, and let's see how we can get our flow accumulation. Okay, so accumulation means the water is all coming from one area and it is coming to one single point, which is our 4 point. Okay, so let us see how this flow accumulation can be done. So it is asking the input flow direction. Just now we have created our input flow direction and output accumulation raster. So what is the name that you want to give for the output accumulation raster? So I'm browsing and I'm going to give the stow flow accumulation. Okay. And then rest all is the same. We are not going to change anything and we are going to click on run. And we are waiting for the system to generate the output. Let me turn off this so that you can see the output. You can see here the output is generated, which is the flow accumulation raster, which means this is the raster in which the flow is being accumulated. And then to delineate the watershed, it is asking us to measure the distance to the output pour point. So let me turn on that output pour point. This is my output pour point. Okay, let me zoom and let me measure the distance. So it is asking me to measure the distance from the pour point to the nearest unit. I request everyone to mute your calls, please. So when we are delineating the watershed, it has to be, the pour point has to be accurate. If you see here, this is our raster image, but whereas our point is located somewhere away from the raster cell, which means we cannot perform correct analysis. That is the reason this point has to be snapped to its nearest raster with the distance. So how do we do that? So let's measure the distance first, and then we will go with the next steps. Okay, so I'm zooming in more. I'm taking from the center. If you see here, I'm going to take it a rounded value here. Okay, it is almost near to 60, 65, so we can take that value. And here we are going to, it is asking us to record that distance, so I'm just taking it as 60 and I'm proceeding with the next step. Let me zoom back. Okay, so let me go to tasks, and here it is asking me to input the raster value or the feature pour point. So we already have our pour point here. So give the pour point, and then you have to give the pour point field. It has only one field, which is object ID. So we are going to take that, and it is asking us one other input for input accumulation raster, because this is the raster and we found that there is a distance between the pour point to the raster. So that is nothing but our flow accumulation raster. So we are taking that, and then we want to give the output raster. So it is nothing but our snap outlet to stream, which means we are snapping the pour point to the stream. So I'm going to give the name here stove snapped outlet, because I'm snapping the pour point to the stream here. So click on save. And what is the distance? Just now we measured, it is about 60. So I'm going to give it as 60, and then I'm going to click on run, so that the pour point is snapped to our stream. Can you see here this green colored one, which means this point has moved from this location to this location based on the distance that we have measured and which we have given here. So now the pour point is on our stream, and you know the pour point is the minimum temperature at which the liquid flows, or the temperature at which the liquid will lose its flow characteristics. So from here we are going to do our further analysis. Okay, so let me zoom back. I know this topic is a bit lengthy, but you will have this recorded version posted on the YouTube, and we will send you that YouTube links to your emails, and then you can watch it whenever you have time. So now I got my pour point snapped to the stream. Now I want to delineate the watershed. So how do I do that? Go to tasks. So you are delineating the watershed, which is your fifth point, and it is asking me the flow direction raster, which we have generated just now. Fill flow direction, and the input raster or the feature pour point. Just now we mapped the feature pour point to our flow accumulation raster, right? The snapped outlet. And here we are going to generate our watershed. So just let me give the watershed name, and let me run. Okay, let me turn it off. So if you see here, this is what our watershed is, which is formed. So let me go here and let me give the symbology. So let me give unique value and let me select the colors for this. I have only one value here, so obviously I can choose only one color. So this is my watershed area. So from here we are going to our next task, which is now we have the watershed area. Now we need to understand at what velocity the water is flowing from the watershed to the pour point. Okay, for which we need a field called as a velocity field. So let me save this. Let me go back to the task. So now we are done with our watershed. Now we have to create a velocity field. So if you see here in the pop-up, you can see what is that velocity field. In this task, you will use your watershed, which means which we have generated and which you can see in the blue color, and the distal elevation raster layers to create a velocity field. And the velocity field determines how fast the water will flow at each point in the raster layer. And there are several ways to create velocity fields. But here, as I told you, we are creating the velocity field by taking spatially variant and time and discharge invariant. So spatially variant means, let us suppose a water is flowing from here to here, which means it is changing its location or the coordinates every now and then. So that is the reason it is spatially invariant. But we are as of now to because we don't have more data on the time and discharge rate, as such we are keeping that as invariant, and then we are going to do our analysis. So let's click on this velocity layer. So if we want to create a velocity field, first thing is we need to have a slope raster. So let us see what is this and then proceed. So here I want to input the raster, and the raster is stow fill, the distal elevation, the final distal elevation. And then I'm going to give the name of the slope as stow slope. And then normally the slope is measured in percentages. So I'm going to give it as percentage rise, and then I'm going to click on run to generate a slope raster to identify how the slope is. All right, so I've got my raster data here, and this is the slope raster data, and wherever you are seeing the darker areas are the areas which has more steepness, and wherever you are seeing this light color or the lighter areas are the areas which are very narrow, which does not have steepness, which means which are very low, and these are like the areas which are having higher elevation. Now we have to calculate the slope area. So for this, as this is a raster data, we need to do the calculation, which means the raster calculation has to be done. So for that raster calculation, we have this here. So for calculating this slope area, what we will do is we will multiply our slope area, slope layer with the flow accumulation. So which means the slope at what rate the water is flow is getting accumulated. So we will take that formula and we will use it here. And then output raster is our slope, stow slope area. And then I'm clicking on run. So with which I will know the slope area. So I'm going to give this, and then I'm going to generate this slope area. I want to do some environmental settings. So I want to just do it only for the watershed area. So I'm just giving this, and then I'm clicking on run. You can see here, this is the watershed area in which we can see that what we call the stow slope area. So this particular stow slope area. So this is all the slope area in which the water will flow and it gets accumulated at this pour point. So now it is asking to limit the minimum velocities. Velocity means the speed at which the water is flowing. So you will have the minimum speed and the maximum speed, because in summers you don't have the water flowing very fastly, but whereas in rainy season or whereas in floods, the water flows so rapidly. So you need to set some minimum and maximum velocity. So you can take like it is up to you how you can set your lower limit and upper limit. So I'm going to set the lower limit here as 0.2, and then 0.02, and then a higher limit as 2, and then I'm going to work here. For this I need something called as a input conditional raster, which means I'm going to give certain conditions. So for this, what I have to do is, what is that condition is, I have to go to the slope area, and then I need to click on the properties, and then I need to go to source, and I need to check the statistics. Can you see this mean area? So I'm copying this mean area. So which means that area I'm going to use for doing the conditional raster here. Okay, so I have copied that value. Now give me that, let me give that conditional raster here. So my slope area, I want to give certain conditions on this slope area only. So for which I want to limit that by using this map algebra expression. Okay. So let me give the value here. So let me calculate the velocity field first, and then so here I have for the formula, so I'm just copying and pasting it here. So here I have to give the mean value. So I will give the mean value which I have copied. And then I'm going to generate. I'm not limiting it here. So it is just I'm calculating the velocity field, which means the water in which at what rate the water flows within this watershed is being calculated here. And then I will limit this it is unlimited, then I will give the limitation lower limit and higher limit in the next tool. Once this tool gets run, I'll be giving the next limits. So if you come back and see here, this is the limit, minimum and maximum limit. So as I can see, like more area is here, so I can go ahead and give the minimum and maximum values within this range. So it is up to you how you want to give. So I'm going to limit the velocities. So for this input conditional raster, so where do you want to limit? I want to limit it in the velocity, the lower limit and the higher limit. So I'm going to give this one, and I'm going to give a condition where value is greater than or equal to. So here they're telling me to give a constant value, which is obviously the very less value which we can give, which is like 0.02. And this is the lowest limit of the velocity. So I'm going to give the lowest limit. So input raster or constant value, the input raster is this velocity unlimited, and I want to give the value as 0.02, and with what name I want to store my output? Stove velocity lower limit. Click on save and click on run. So this is going to give me the lower velocity at which the water will flow to the pour point. Okay, so now if you go back and see, the lower limit is 0.02, but the maximum value is still the same, 8.00183. But I want to limit the higher value also. So I can give that limit. So I'm going to take the conditional raster. Again, I'm going to give the value. So here it should be, because earlier it is greater than, now it should be less than, because I'm going to give the value less than 2 here. And then you're going to give your raster, which is the lower limit, and the constant value as 2, and then output raster. So this is your velocity, because this is the maximum velocity at which your water will get flown here. So click on OK and click on finish for the system to run, and just wait for it. If you see here, earlier you have seen very less number of streams, but if you see here, now you are seeing more number of streams, because you have limited the higher value, lower limit and the higher limit. That is why you are now seeing more number of streams. Earlier you did not see those many number of streams. You have limited the values, that is why you are able to see here. So let me save. So let me go to the tasks. So now we are already done with the velocity. So we are done with the digital elevation, removed the errors. From that we have generated watershed, and from that now we have calculated velocity field, and then we have set the limits of lower limit and higher limit, and now we have to create an isochrone map. So isochrone map is nothing but the inverse of your velocity layer is nothing but your the weight that which we are going to give for your isochrone map. So let me give the expression here. So my velocity layer is stove velocity, so that is the reason I've given this. And what is this we are going to generate here? It is nothing but the weight, create a weighted grid. So we're going to create a weighted grid raster. So let me give the name as stove weight and click on OK and click on run. So now you can see it clearly that weights have been added to our velocity, where we have set the limits as upper limit and lower limit. Okay. Okay, let us proceed with the next one. Extract flow direction. As you all know how we can do this flow extraction. So the input raster we have to give, and then we have our flow direction as our this one, and then we have to mask the data with our watershed, because I don't want to do any analysis out of the watershed. So just the watershed, and then I want to calculate the watershed flow direction here. So I'm going to give the name, click on save and click on run. For input raster, select the flow direction, so which we have already done. For input feature, mask it with the stove watershed, which we have already done. And then the output which I'm going to get, I have stored with a name called flow direction, watershed flow direction. And then I'm just clicking on run for the tool to generate and show me the direction, flow direction. So let me save this. Let me go back, and if you see here, as you know, you'll have only 8 directions. So you have got 8 different directions with 8 different colors for the flow here. And then SS flow time. So the flow is okay. Now you have to know how much time is it taking for the water to flow from different areas to the pour point, which means to the red dot here. So for which I need to input the flow direction raster. So let me give the watershed flow direction, and I have to give the name for the output. So here I'm going to calculate flow time. So let me give it a stove time. And obviously the water is flowing towards the downward direction, but we have already generated a weight earlier. If you remember, this is the one. I'll turn off this. This is the weighted one which we have limited by lower and higher values. So let me give that as an input here for the input weighted raster. And now click on run, and this will generate me the pour point, access flow time to the pour point. How much time does it take for the water to flow from different directions to the pour point? So now you have this. Let us go back and see what this has generated. So this has given me, for the water to flow within the watershed, it is taking about 3,47,518 seconds for the water to flow to the pour point. So obviously you can convert that seconds to number of hours, and then you will get to know how much time is it really taking for the water to flow to the pour point. And then let's come to the tasks here, and input the raster. So what we are doing, it has given me some color. I just wanted to reclassify it to the if you see here, it is just a single class. It is giving me a range, but I want to group it. I want to divide the time and then group it, reclassify flow time into the zones. So for which my raster would be like the stove time. And then here it is asking me, you have to reclassify it. So how do you reclassify all these values? So you can give a range like 0 to 100, 0 to 1000, 1000 to 2000, like that you can give a range. And we have already got that range. So from 0 to, from to what? To this 1800 seconds. So it is like value to value, you're going to give it here. Okay, and then you're going to take this input. See, you have given different values within the range you can give, and then you have to browse this for the reclassification of the data. So come here and then browse the data. This is the one. So which obviously 0 to 1800 seconds. So it maps to 1800. So all values will map to 1800. From 1800 to 3600, all the values will get mapped to 3600. Like this, all the values are getting mapped. And now we have to classify this. So we are classifying the flow time which we generated into isochrone zones. So we are generating stove isochrones. This is our fourth step. So here I'm going to click on finish. So here it has taken 48,600, but my value is 347518. So three four seven five one eight. Okay. So I can resave it because I have extra value. So I'm just giving that other one as well. And then I'm clicking on finish. Let me save. Let me finish. Now we will get this isochrone layer. If you see here, we can actually give the symbology and then it will follow properly. So let me go here and let me click on symbology and let me give unique values. So let me go to analysis. So here what I will do is I'll go here and then so 347518. So let me give the value here. Nine 8600. So you can classify as if you want. There is no specification that you have to do this way. It is based on how many classes you want and how you want. Based on that, you can do it. Let me give the values here quickly. So here we are not doing anything. We are just classifying the data into different classes. That's how we wanted. As I got more values, I'm just generating those values here. So let me rerun the tool once again. So here I have given this start time values, and then I'm going to browse and give this value. Let me check if it has populated correctly. And then now I have to give this output value as I have already given earlier. Let me give it as 1. So, and then click on run, and let's see how the data will come up. So you have to take more number of ranges here, then obviously your this watershed will give you more number of colors, because I have given very large ranges here. That is the reason it is showing me like this. I'll remove this. And then right click, symbology. And then I'm going to take unique values. Okay. And if you see here, everything is coming here and it is stopping here. This is where like we call it as that 4 point. So click on save. Now we are in our last step. So which is our unit hydrograph. So it is asking me like convert the isochrone map into a table. So whatever we got just now, that has to be converted to a table here. So select the isochrones, and then your output location is your geodatabase where we are saving the data. And this isochrones table I want, isochrones 1 table. So I'm going to give that one. And if you want, you can give conditions, but as of now I don't want any conditions to be given, so I will just click on run. So it is asking me to give an increment area field, which means like I have this. I'm opening the attribute table. So it is just giving me the count here, but I want to add field like area and all, so I'm going to give that area here. This we converted into a table, right? So this is the table. It is the same table we have. Okay. So here we are going to create that area incremental field here. So I'm going to take the table as my input, and I'm going to give the field name. Obviously area will be more, so I have to take this double. So I'm going to give this in square meters. So I'm going to click on run. So as soon as I run this, I should be able to get that area field here. So field has been added in the previous step. Now I have to calculate the area. So obviously the area which we are calculating here is for this isochrones 1 table. So take that, and for which area you want to calculate the field, you want to calculate the field for area. So you can give the area here, area meters, and then you can calculate the area here. So I'm just so count into 30 by 30 which I'm giving here. So this will help me to calculate the area field in square meters. So let me give that and click on let me check, and if it is okay. So now the area has been converted into the square meters. Now it is asking me to add a unit hydrograph field here. So for which again I have to click on adding a field. So for the same table, what is the field I want to create? I want to create like unit hydrography ordinate. So and here I'm going to take the field type double, and then I'm going to give the alias name unit hydrograph ordinate, and then I'm going to click on run so that one more field will get added up here. So this unit hydrograph ordinate has been added. So for the input table, you're going to choose the standalone table, which is the stow isochrones table 1. And for which field you want to calculate now, you want to calculate for unit hydrograph ordinate. And then you're going to select, and then you're going to give the formula. So this area by 1800 will give the unit hydrograph ordinate. So let me give that. And click on finish. Now this field is getting calculated. Okay. So I got this unit hydrograph ordinate. Now we have to plot that unit hydrograph for understanding the how it is being distributed. For which I have to go back here and then select this table, and then I want to go to so I am going to this standalone table, and here I have a chart, and in this I'm going to select the line chart. So it gives me the change or a continuous range such as time or distance. So I'm going to take that line graph. So here I want to take the value, and then the numeric field which I wanted to plot is this unit hydrograph ordinate, and click on apply. So if you see here, as we have given the range at the end, different ranges, you can see how the ordinate is there, which is varying at the bigger scale here, because here you have given the range between the range of values is more when you compare the last values. That is the reason it is showing more deviation. But if you give less, it will show you different variations here, and at small intervals also you can see the change. And so let me go back. Okay. So here I want to change the name and everything here, so I can chat properties, and I can go here and I can change the name. Unit hydrograph at the outlet point. For x-axis, this is the time in seconds, because whatever we have generated is in seconds only. And for the y-axis, we are going to give, this is basically the discharge at outlet unit. As this is in square meters, this also should be in square meters per second. You can see here. So we have generated this hydrograph for the number of seconds at which the discharge at the outlet per unit of rainfall is there. So at this discharge point or the pour point, what is the time that is taking for the water to flow is what is given in the unit hydrograph. So let's go back to tasks and see what we have done. So we have created precondition for the elevation model to remove the errors in the digital elevation model. And we have identified sinks and filled the sinks. Then we have taken this watershed. We have demarcated the watershed by using the flow direction. And then based on that, we have created the velocity field where we have given the limits of the lower limit velocity and the higher limit velocity. And then to that velocity, for generating isochrone maps, we have given certain weights, and then we have generated the isochrone map for the watershed, which tells us like how long does it take for the water to flow to the outlet. So as we have got the uh, uh, time for which we flow the water gets flowed to the pour point, now we have generated a unit hydrograph. So if you have any questions, you can ask. We are open to questions. Any questions? So if you don't have any questions, we'd be. Yes, because these tasks, whatever we have, these are like a set of steps. Normally, we can identify in our toolbar and we can do it. But if you want uh, people to do the process at once, you can create those tasks so that like the workflow is streamlined. If you remember, like at one point when I got an error, and if I when I wanted to reclassify all this, what I have done is I have gone back to analysis tools, and then I have rerun this reclassify tool. So basically what we are running, if you see here, I have generated a watershed and then slope and then a conditional, this one raster calculator. So these are already existing within our RGS Pro tools. So what we have done is we have like just our model builder, like how we connect different tools together, and we just give few inputs to generate the output. So the tasks are similar to that, which will help us to tell like from which step to which step we have to do. As generally this task has to be completed, our session tech talk has to be completed in 1 hour, but today we have taken like almost like 1.5 hours, even when the tasks have been there, because it has taken so much of time uh, to get the process done. So for a new person, if they have to explore and do it, it will take more time when they have to search the tools and then get accustomed with the tools and then use it. That is the reason we created the task, and then we are running the tools within the task. Is it possible to show the procedure? How could we create it? So all here, what are the inputs that basically we have is you have just one pour point, the boundary where you want to work on your uh, flood prone areas. That is the one which you have to take, and the other input which you're going to take is your surface water, which you just digitize the water bodies in your given location, and the digital elevation model which you download from the USGS uh, Earth Explorer website. So these are the only four inputs that you need. One, DEM, digital elevation model. Second thing, the surface water which you digitize. And the third is the pour point at which the water flows, accumulates, and then comes and stops at one particular point, which is your pour point. And then the boundary for which area you want to do. So these are just the four uh, different inputs which you need. Thank you, Siddharth. So any other questions, please? All right, see you again then in the next Tech Talk, and we'll be sending you a feedback form, and I request everybody to fill out that feedback form, which will help us to do improvements in our presentations or in our Tech Talks, and come up with different kinds of topics that you are looking out for. Thank you, everyone. Thanks, Abhay.
Thank you.